Welcome to SPC Insights with Dr. Bill, simplifying SPC and statistical analysis. This video is going to compare 4 different normality tests. Suppose you have a statistical test you want to perform. The test requires your data to be normally distributed. How can you find out if it is? You can do a histogram, take a look at it and see if it's bell-shaped, or construct a normal probability plot, do the points fall on a straight line, or you can run a normality test, which we're going to do in this video, and use the p-value to determine if the data is normally distributed or not. We're going to start with what the hypotheses are, example data, then we're going to cover the 4 tests, Anderson-Darling, Kolmogorov-Smirnov, Lilliefors, Shapiro-Wilk, and then decide which is best and summary. And we're actually going to give you the answer to start with, which is best. The data we use in our example is not normally distributed. So we have our normality test, the 4 we're going to look at, the statistic we're going to calculate, the p-value, and then our decision, is it normal or not? You can say 3 of the tests say it's not normal, while 1 was. 1 does say it's normal. And the KS test incorrectly assumes that the data are normally distributed, while the other 3 point out the data are not normally distributed. So which one's best? We're going to show you Shapiro-Wilk's test is the best. It's good for sample sizes less than 5,000. Anderson-Darling's next, very powerful, especially in the tails. Lilliefors is third. It's more powerful than the KS test. It takes into account the average and standard deviation from the sample, where the KS test assumes it's the true average and standard deviation of the population, which you don't usually know. So what are our 2 hypotheses? The null hypothesis is that the data follows the normal distribution. The alternate hypothesis, the data does not follow the normal distribution. And our approach is going to be calculate a statistic for each of the 4 normality tests and a p-value for each of the 4. Now remember, p-value is the probability of getting a result that's more extreme if the null hypothesis is true. If that value is small, typically less than 0.05, you conclude that the data are not normally distributed. If it's large, typically greater than 0.05, you conclude that the data are normally distributed. So let's take a look at our example data here. We have 50 points, and we're going to start by making a histogram. Does this look like a bell-shaped curve to you? Does this look like it's normally distributed? Taking a look at it, and it really doesn't look normally distributed to me. It doesn't look like a bell-shaped curve. But let's talk about a normal probability plot and see what that looks like with our example data. So again, here are our example data, and here's the normal probability plot. We have the z-value on the y-axis, the value on the x-axis. Do the points fall on a straight line? Well, some of them do towards the middle, but definitely on the tails they're falling away from the line. So let's look at the Anderson-Darling statistic. It was developed in '52, and it compares the actual distribution of the data to what you would expect if the data were normally distributed with the sample average and sample standard deviation. So you can see, like here is the red, that's the true standard deviation, and the blue is our actual one. So steps in it, you're going to sort the n samples from smallest to largest. I equal 1 is the smallest value. Calculate the average and standard deviation. Standardize the data by calculating C, each of the x values minus the average divided by the standard deviation. Then you're going to calculate the cumulative distribution function for the normal distribution for each z value. It measures how far the data are from the expected value of the normal distribution. You can use norm-stist in Excel to do that. Then you calculate the AD statistic, which is shown here. Then the higher the value of AD, the less likely the data is to be from a normal distribution. Puts more weight on the differences between the sample data and true normal distribution in the tails. And then you adjust it for the small sample size, and that's called AD star. So here's a probability plot with an Anderson-Darling statistic from the SPC for Excel software. AD is 0.8653, AD star is 0.8791, and the p-value is 0.0245. Now we calculate that p-value based on the value of AD star. The value of AD star in our example is 0.8791. That falls into the range of the first bullet, gives a p-value of 0.0245. And since that's low, we assume that the null hypothesis is false. Now, the KS test was developed by 2 mathematicians. It's a non-numeric test used to determine if sample comes from a normal distribution. It can be used with other distributions too. It compares the empirical distribution to the cumulative distribution function. So the steps in it. Again, you're going to sort the values from smallest to largest, calculate the average and standard deviation, standardize the data again. Then you're going to calculate the empirical CDF, and that's simply I divided by N, where N is the sample size. Then you're going to calculate the theoretical norm distribution, CDF, and you're going to use norm S again. Then you're going to calculate something called D plus and D minus. And D plus is the maximum positive deviation between the empirical CDF and the theoretical. D minus is the maximum negative one. And you can then calculate D, which is simply the maximum of D plus and D minus. And that's the KS statistics. So here you can see the KS chart from the SPC for Excel software. KS is 0.1515, E is 0.0188. So there are tables that you can compare the value of D against to determine the p-value. You can also do it in the formula which converges very rapidly. The p-value is 0.1844, and you would conclude then that the data are normally distributed. But this is different than what we got for the Anderson-Darwin statistics. Why is that? Well, with the KS test, there are problems with the p-values. It's conservative when used with the sample average and standard deviations, which is all you usually have. It's designed really to work with the true values of that, which we don't know, and it leads to wrong results. Well, the Lilliefors test takes care of that problem. It was developed in 1965 by American statisticians. What he did was adjust the critical values of D to account for using the sample averages and standard deviations. And those typically come from a table. So the difference is in determining the p-value. The value of D is the same as for the KS test. So you're going to look up those critical values in the table based on N and alpha. So you compare D to D critical, and in this case you see your KS value is still 1515. The Lilliefors shows a probability of less than 0.01, so the data does not come from a normal distribution. So let's look at the Shapiro-Wilk test. It's just as used for the normal distribution. It's not used for other distributions. What you do is, again, the steps in it, you sort the samples to begin with. Then you're going to do a lot of calculations. We're going to show the equations here, but you need to go to the website to see all the details. The link shown here, calculate MI and M. Going to calculate AI coefficients. There are a lot of equations in this to do this. Of course, the SPC for Excel software does it automatically for you. And then you're going to calculate W, which is the statistics for the Shapiro-Wilk test, and then calculate the p-value. And in this case, the p-value is less than 0.05. It's 0.0191, and that tells us again that the data are not normally distributed. So which of these four tests is best? We said the data was not normally distributed. We had our four tests, showed how to calculate the statistics and the p-value and make a decision. KS test said it was not normal, and the rest, it was normal and the rest said not normal. So Shapiro-Wilk and Anderson-Darwin are the best tests to use in this case. Hope you enjoyed the video. You click on the YouTube subscribe button, visit our SPC Knowledge Base online, 240 articles. You can use our software to make your own control charts and other statistical tools, including the normality plots. Thank you for watching the video.